Thanks for having me. I'd like to talk today about some of the work I finished up my PhD at NYU on, and that was with Rob Fergus there. And this started off what is now Clarifai, a new startup here in New York specializing in image and video recognition. So as an overview, I'm going to describe a technique to visualize convolutional networks. And convolutional networks are a way to recognize objects in images and video. And what we use to do this is something called a deconvolutional network, and I'll get into that in a bit. So with this visualization, we can actually understand what each layer is learning now, and from that, gain some insights to improve performance. So what are these models? Convolutional neural networks. So they're not new. They've been around since around '89 by this fellow, Lecun, who is a professor at NYU, and he's heading up the AI group at Facebook now. And he came up with the idea to apply neural networks over small regions using a convolution instead of over an entire image using a fully connected layer. So it looks something like it's shown on the bottom, where you have convolution layers, and you have some nonlinearity that just allows the model to learn more robust functions than linear functions, and a pooling layer, which is typically max pooling these days. You could do things like average pooling as well. So that process of convolving, taking nonlinearity, and pooling is repeated several times until basically the spatial information is pooled out of the image, and you get a final output layer that gives you a probability over all the categories you're interested in recognizing. And this is all trained by backpropagating your classification error. So when you make a mistake, that error is backpropagated throughout the entire network to update the parameters. In a real example, when you show it an image, you would do convolutions, pooling, and repeat that. I didn't show nonlinearities, but the probability would be something like that, where it's highly confident there's a boat in this image and less likely that there's a dog, a cat, or a bird. And there's really a bunch of pioneers in the field. Two notable ones were Lecun and Geoff Hinton. And these ideas behind neural networks have been around since the 80s when these guys started working on them. And even before that, into the 70s. And the new approaches that are giving breakthrough performance numbers have very much the same architecture as was around in the 1980s. The main difference was around 2009 when GPU computing became mainstream and applied to machine learning. We could get a 30 times speed up, and that was crucial for allowing us to train on much more data and much bigger models. And when you do that, you can make the models much more powerful and understand a lot more about the world. It also helped with experimentation because we could iterate on experiments much quicker. And the big companies have noticed this. So Geoff Hinton was acquired by Google. He had a small startup recently acquired about 2 years ago. And Lecun is now heading up the AI group at Facebook since last December. And the results that were really a breakthrough in this field were by Geoff Hinton. And that's why Google acquired them quickly after these results. It was by two of his excellent PhD students, Alex Grashevsky and Ilya Sutskever. And they did something like this. So I'm showing here error rates on a common benchmark called ImageNet, which is held every year. And the benchmark is to recognize out of 1,000 different categories which objects appear in an image. And you're given a training set of about 1.3 million images, a held out validation set for 50,000 images that you can play with, and then a held out test set of 100,000 images that you never get to see the labels for. So it's a fair comparison in that sense. And the 4 bars to the right are traditional computer vision methods. And the goal here is to minimize the error rate. And you can see the supervision team out of Toronto use a deep neural network instead of a traditional computer vision method. And it was basically a step function in terms of performance. Dropping it by 10%. Instead of 26, it's down to about 15%. So this is a revolutionary result that has really changed the whole field of computer vision, and many people in that field have now switched to using neural networks in their research. Another nice result that recently came out was this group out of MIT that compared the performance of these deep neural networks to that of a primate and a human. And they did that by creating a data set, like shown on the top, with 10 images, or 10 categories of objects put on top of random backgrounds with different scales and rotations of the objects. And then they were presented to a monkey, and they actually opened up the monkey's brain and implanted electrodes. And when they were presented with the objects or the images, then the electrodes would fire in some certain pattern. Those were recorded, and then a simple linear classifier like an SVM was trained on top. And the goal was to see if from these electrode firings you could actually recognize these objects. And they compared that to some of the deep neural networks and also humans. So here is the monkey's V4 layer. So the visual cortex is thought to be decomposed into layers. And this is some intermediate representation. So using that, you can get about 40% accuracy with the extrapolation. The extrapolation is because they only recorded about 300 electrodes, whereas there's billions of neurons or more that they could have recorded. So they extrapolate a bit. Looking at IT cortex, this is much deeper into the brain and has a lot more reasoning involved about the objects and the scene. And you can see a massive performance boost, and it's nearly 75%. So then they compared to humans on Mechanical Turk, presented with the same images. And a key thing here was they were presented for 100 milliseconds. And any one of us in this room who saw these images for more than that would be able to get nearly 100%. But in a rapid presentation, you're only using a certain part of your brain that can do a feed-forward pass, which is very similar to these neural networks, and you can't do a lot of reasoning. So the performance is not quite as good. Nearly that of the IT cortex of the monkey. Then they started comparing machine learning and computer vision models. So V1-like models are basically edge detection at different orientations and different frequencies. An HMax model combines that with some pooling so that you don't really care exactly where these edges are in the image. It's a little bit invariant to that. A model out of the Google Brain group. This was trained without any labels to learn some interesting features and then applied to the classification task. Didn't perform that much better. And then this is the Toronto group's result that won the ImageNet competition. So you can see a massive boost in performance, actually surpassing the monkey at this point. And then this was Rob Fergus and I out of NYU. And this is showing that these models now are actually at the performance of not only monkeys, but actually humans when you're presented with images at a rapid pace. And the nice thing about this is when these models are run on GPUs, you can actually run them significantly faster than 100 milliseconds. So we can actually perform at human levels and do it faster. But with all these nice results, it's not really clear what these models are learning. So that's what Rob Fergus and I really wanted to solve and dive into. So we did that using a technique called deconvolutional networks. And this is something that Rob and I did for the first few years of my PhD. And the goal of that project was to create an unsupervised learning model. So we didn't care about labels. We just took the image as the input and tried to reconstruct it while making the top level features very sparse, so using very little of them. And it was a completely top-down model in order to do that reconstruction. And it was an inference method like sparse coding to kind of infer these features that reconstruct the image well and are sparse. And we used all the same components as convolutional networks. We used convolutions, but using a transpose of the filters. We used nonlinearities, and we used unpooling, which I'll describe next. And in this work, where we visualize, we don't do any of this optimization. We basically use this as a tool to just look into a convolutional network's features and then reconstruct them down to the image. So one important part to get this reconstruction very clean and sharp is to make the max pooling operation that you have in convolutional networks to be reversible. So when you're going up in a convolutional network, you have something like this, where there's a bunch of activations. Longer bars are stronger and smaller are weaker. And you usually do pooling over local regions, say 2 by 2. So doing max pooling, you get something like this where you keep the strongest element, and you can do it with or without keeping the sign. In this case, we're keeping the sign, taking the strongest absolute value. And what we also do in order to reverse this is store where that value came from. We call that the switches. And that allows us to take any new value that we're using during the reconstruction and plop it down in the correct location, and setting all the other locations to 0. This is really important for getting good reconstructions, especially when you have multiple layers, because if you arbitrarily pick a location, you're really losing all the edge information in the image. So that really makes the image that you're reconstructing blurry. And you actually get a lot of different color variations as well. So if we look at what these models are learning, starting at the first layer, you see something like this. So we're looking at a convolutional neural network's first layer filters. So these are what are convolved directly with the pixels. And you can see it's a bunch of oriented edges. This is what people find in the visual cortex, actually, in V1 type of layers. And you can also see color blobs and color edges at different frequencies and different orientations. So this is nothing new. People knew that these models and many other models learn the same type of features from pixels, but it's just showing you what it looks like. But nobody really knew what was going on above that. So to do that, we want to project from the higher layers back down to get some visualization of what those higher layers are doing. So what we do is we take an input image, we run it through the convolutional network, feedforward. That gives us some activations over all the feature maps at whatever layer we want to visualize. This could be the third layer, for example. And to visualize them, we select a single feature map at a time that we want to look at, and we take the strongest activation in that feature map for that image. And that gives us an idea of what part of the image and what in the image actually activates that feature really strongly. And we use that as input to the top of a deconvolutional network that uses the same filters from the convolutional network and also the same switches from all the max pooling layers in the convolutional network in order to reconstruct top-down to give us a visualization. So it's really crucial that you use the same filters, use the same switches, and take a strong activation. But we don't just look at a strong activation for one image. We want to see what this feature fires on through a bunch of images to learn not only what most strongly activates it over a whole data set, but also how it's invariant by looking at a set of these strong activations. So we run it through a validation set of 50,000 images, and we take the max activation for each of the feature maps over the entire 50,000 instantiations of it. And that gives us the strongest activation that we visualize downwards using the switches for the image that that activation came from. Then we look at the second strongest activation out of all 50,000 images, the third, fourth, and we'll show you up to 9 of the strongest activations. And you'll see how that can show some type of invariance that that feature has learned. So what I'm showing here is looking at the strongest activation in the first layer feature maps. And the colorful plot is patches out of the image. So these are pixels out of the image right above where that activation fired strongly. And they correspond to the filters that are shown in the bottom left. So if you look at the top left filter here, it's almost horizontal. And you can see the top left 3 by 3 region here are all patches of horizontal type of content with different colors. And the top left of that 3 by 3 is the strongest activation throughout the entire 50,000 images and all the spatial parts of the images for that one filter. And then the second row, first column, is the second most strong activation out of the entire data set. And so forth, all the way to the 9th strongest. And you can see for comparing the patches to the filters, it's doing what you would expect. It's firing on when those pixels line up to how the filters look like. And same with the colors, you can see it lining up, not always in an obvious way, but in some way either positively or negatively correlated with the colors of the filters. Now it gets more interesting when we go to layer 2. So this is something that wasn't obvious what was happening. Everyone could look at the raw coefficients in layer 2 or the raw coefficients in layer 1, but before this, they haven't really seen what's going on in the second layer. And you can see it's learning a much more complex set of patterns than the first layer edges. And you can see it's combining them in meaningful ways, like parallel lines, curves, circles, T-junctions, grading patterns, colorful blobs. A huge variety of different structure is present in already the second layer. And you can see it covers a much larger space of the image because it's gone through the first layer convolutions, then there was a pooling layer in between the second layer convolutions. So it has a much broader scope of what it can see in the image. And that's represented when we reconstruct down, we get a larger reconstruction that's right above where the strongest activation in the second layer occurred. Now this is showing all of the 256 different feature maps in the second layer. So this is giving you the strongest activation for each one of those. But we can also look at a handful of randomly selected ones that are showing not just the strongest activation, but the 9 strongest activations. And you can see that it's exhibiting the same type of grouping behavior that you saw in the first layer. But it's getting more complicated, the grouping. So you can see, because of the pooling in the first layer, after the first layer convolutions, these features are pretty invariant to small changes. You can see down here that a small dot and a circle and a spiral all fire this same second layer feature very strongly. And you can see even here, text-like features or strong grid patterns fire that feature. And it can be invariance to different orientations, can be invariance to the tightness of circles, different colors. There's a bunch of different invariants that's already encoded by the second layer. Now, looking at these, it's hard to tell what something like this might represent in the image. But what we can do, because we know the exact location of where we started the reconstruction from and all the pooling switches going down, we can crop out the part of the image where that came from. And if you flick back and forth, you can see that these purple-like regions are actually skin color. So by the second layer, it's determined that skin is actually really useful to have as a feature. Just below that, a slightly brighter red type of shade is actually some kind of fiery looking thing. You can see other grouping like circles over here, or the circles down there, blue type of patterns. So there's grouping by color or by shape. Moving to the third layer, it's getting more and more complex. So this has now gone through 2 pooling layers and 3 convolution layers. So it's seeing about 80 by 80 pixels in the original image, which was around 224 pixels. And now you can see it's starting to learn object parts, things that are important for building up a representation of an object. You can see in the top left things like a dog's face, a human face, eyeballs, a baby's face, some texture regions. You can see it's, again, much more complex than what the second layer was. We can do the same type of examination of the 9 strongest activations, and there's a lot of grouping as well. But it's more grouping not at the very low level edge type of information, but more semantically relevant things like people's faces or different types of grid patterns, but not all the same type. Or even this one up here, which has a strong green tinge to it. If we look at the patches that correspond to that, it's grouping fire together. If we look at the bottom middle region, it's kind of hard to see what this is from the visualizations, but if you look at the patches, It's learning a cloud detector, essentially. And even categories of visual content that aren't actual categories in the task, such as grass, is actually being learned as a strong feature by the third layer. Moving to the fourth layer, the same story applies. This time there was no pooling between the third and fourth layer, so the size of the receptive field that the fourth layer sees in the image has not grown that much. But the content is getting more and more object specific. You get a lot more fully formed faces of dogs and humans and other large object parts. If we look at the 9 strongest here, the groupings now are almost not at all structurally related, but more semantically related. For example, the pose of these dogs is not exactly overlapping anymore, but you can see that this whole feature just fires on dogs of different breeds. This feature below and to the right is firing on a variety of different eyeballs. I think they're all dogs. But the feature up and to the right is firing on a combination of dogs and monkeys that have very similar faces. One other interesting one in the fourth layer is the bottom middle, where you see these strong green activations. This is actually small green locations in the image. And before doing these visualizations, we never thought that would be something that the model thinks is important. We thought color would be washed out very early on or be a very blurry feature. But it's really localizing exactly where that feature in the image is. And it's kind of incredible that it can do that all the way up through multiple pooling layers, multiple convolution layers. And we didn't expect that. The final convolution layer is a fifth. It again did not go through any additional pooling layers, but it's getting slightly larger because of boundary effects on the convolutions. And it's getting closer to the classification layer, which is still another couple fully connected layers on top of this. And because it's getting closer to having to make that decision on what class the image belongs to, the content in this layer is getting more and more object specific. If you look at the breakout here, just below the number 5, you can see a bunch of interesting patterns. And those are actually keyboards of different types at different orientation. That's something, again, we didn't expect to see is rotation invariance. These models don't have any explicit rotation invariance. They have a lot of shift invariance because of the convolutions and the pooling. But there's no explicit way to represent rotation. But one way you can actually do that representation is using max pooling locations by taking, if you consider the local regions, you can move a max pooling location a couple pixels over and then a couple pixels to the right and then down and to the left. And that'll give you some rotation invariance very locally. And as you do this at higher and higher layers, you can encode that in the model. Another interesting feature in this layer is right next to the keyboards, there's some hazy looking blob. But that's actually a background water detector. And water itself is not a category, I believe, but it's important for doing things like recognizing seals or bathing suits or ships. And finally, another interesting one here on the right is all these dogs. It's actually learned basically a husky detector by the 5th layer. And there's only 256 features in this layer, but it's realized that that is unique enough and important enough to have that it basically allocated that representation for that feature. And again, nobody's done this kind of allocation. This is all learned by the model. So another experiment we did before actually doing the crops out of the image, we just looked at the visualizations before doing this experiment. We wanted to confirm that the visualizations were actually triggering on parts of the image that make sense. So what we did is take a block of zeros essentially, and actually the mean pixel 128, and run that over the image. And at every location of that block, we recorded certain parts of the activations or the probabilities of the model. So for example, on this image, we took the gray block and slid it over, and on the bottom left, we're showing you the probability of Pomeranian, which was a true label assigned to this image. And each pixel of that bottom left figure is a location of the block over the image. And you can see when the block is over the face of the Pomeranian, the probability of Pomeranian significantly drops, basically to 0. And at that same instance, what we're showing on the right is what is the most probable class out of 1,000. And at that time when the block is blocking the face, then the most probable thing it's guessing is tennis ball, which is a reasonable guess if you consider blocking out this region. So you can see it's really localized on the face and finds that important for recognizing this category. And the reason we picked this image is because out of the visualizations, it was one of the strongest ones that fired one of the fifth layer features. So when we look at that feature map as we slide the block over the image, we can look at the activations and how strongly that feature fires. And you can see that because the visualization showed us that it's triggering on the face of these animals, it drops significantly when we cover the face. So it's kind of confirming that the way we select the visualization is actually showing us what we're expecting to see. A different example, this is a true label as a car wheel. It could be many things, but when the car wheel is blocked out, you can see the probability drop significantly, saying that the model's really localizing where the car wheel is. And the most probable class is kind of scattered because there's many things you could label this image. But an interesting thing we saw is that the strongest feature that we looked at was the one with the number 880 AC. And that came from this image, as you can see. But when we block out any text in the image, it's actually dropping that feature significantly. So it's giving you some notion that the fifth layer has learned a text detector. And you can see from the other features that are visualized here, not from this given image, but from other images, it's firing on all kinds of text, different languages even, or different fonts, different colors, different orientations. So this is really interesting because text is not a category in the model, but it's learned that when you recognize text, it can associate with other classes. And another interesting one is this example, which was labeled Afghan Hound. And when you block out any part of the dog, then it obviously drops the probability of Afghan Hound. But when you block out the faces, it actually increases the probability of the hound. So it's showing you that there's some competition here over what is the true label in this image. And if you block out either of the faces, it's more confident that it's an Afghan Hound. And you can see it jumps around all over the place. And when it jumps, it actually goes to a lot of categories. So faces is not a category in the 1,000, but there's a lot of things that are really associated with faces, like fur coat or mortarboard or academic gown or neck brace that always come up when you show people's faces, and especially when you block out the dog. And that's actually one of the features in the fifth layer is faces. That is really invariant to the type of face or the gender of the person. And you can see it firing or localizing exactly where those faces are. So this shows you kind of what is being learned in all these layers. But now how can we use this to actually improve the performance of the system? So we took the Toronto Group's model, which won the ImageNet challenge in 2012, and we visualized it. And what we saw right away is on figure A here, we saw a huge disparity between the normalization of the filters in the first layer. You can see one really bright white one, and a bunch of very dark ones that do have some structure, but they're just normalized completely differently. So we noticed that we do need to do some kind of renormalization in order to fix this problem and help all the features learn the same. So we looked at, after we fixed that, we looked at what they're learning now, and you can see very specific filters. So very high frequency structured data, and also a lot of dead filters. So we weren't sure why that was, but our guess was that the filters were too large for this first layer because they chose to use 11 by 11 filters, and that can capture a large part of the content of the image when you look at 11 by 11 patches. Visualizing the second layer, we also saw a huge amount of blocking artifacts. So this was a key finding because we noticed that it's losing a lot of information here. And you can see that as well by having a lot of very simple second layer features. So what we did was we renormalized the first layer filters so that they would never go outside some threshold of root mean squared values. And that makes all of them kind of compete evenly with each other, and that gave us figure B here. Then to fix the very specific filters, we just made them smaller. Instead of 11 by 11, we used 7 by 7. That keeps them a lot simpler, but you can still see it's learning a huge variety of content. Different colors, different orientations, and frequencies. And to help with the blocking artifacts and make the second layer much more useful, we made the strides in the convolutions, which are how often you apply this filter in the first layer. We moved that from 4 to 2, and that completely removed the blocking artifacts and also allowed the second layer to be a lot more flexible and learn much more interesting content. So that helped us win a 2013 ImageNet competition. And you can see the results from the Toronto group on the far right. It was around 16.4. And then there was a bunch of different entries, some from large companies, some from other startups, some from top research institutes around the world. The CF entry was actually Rob and I out of NYU. And then the Clarifai entry was me starting up the company. And there's kind of two entries, one just with the original training set and the other with a little bit of extra data, also from ImageNet, but different categories. So these same tricks that we used to reduce the stride and the size of the filters also were used in this year's competition to give very good results. Actually, all of the groups moved to this approach, and the top 5 at least. And even smaller filters were used to get really good results. I got second place in classification and first in localizing where the objects are. And also Andrew Howard had some interesting results using much smaller filters and smaller strides. And even the visualizations have been reused for determining saliency, because if you look at where the visualizations are firing, they were not always covering the entire object. They weren't necessarily useful for detecting a bounding box around an object, but they were useful for understanding what part of that object is used in the network to recognize it, such as the Pomeranian's face. So if you wanted to get a Pomeranian bounding box, it wouldn't be very useful, but for finding the saliency of Pomeranians, you can use the same technique. And the last thing we wanted to look at was how well do these features generalize? So we took a model trained on ImageNet, which has 1 million images, or 1.3 million images, and applied it to a different data set called Caltech 256. And that has less categories, 256 of them. Some of them are overlapping, some of them are not. And the previous state of the art was something, these two results shown in green and red, and the top end was around 55%. So what we looked at is taking this pre-trained model, the filters and all the layers learned on ImageNet, what we could do with very few number of training examples. And with only 6 examples, we were actually matching the state of the art. So it's showing that these models really thrive when there's lots of training data, and they learn features that are important in general for object recognition, and then it can be transferred to other tasks and other data sets very easily with very few new examples. And you can see when you do have lots of new examples, they significantly outperform what you can do if you train on a small number of examples alone. In table format, you can see the previous two results were going up to about 55%. If you just try and train on the Caltech 256 dataset with an ImageNet size model, large convolutional network, then it really struggles. It can't actually learn the features properly because there's just not enough examples. These models have somewhere near 60 million or 70 million parameters, and the Caltech 256 dataset was around 10,000 images only. So you can see that there's a huge several order magnitude difference between the number of parameters you need to learn and the actual amount of content you can learn that from. But if you use a lot more content, you can learn powerful features and reuse that for other tasks. And you can see a huge jump, not only from the state of the art, but a massive jump from what you can get just training on that data. The other investigation we did was to look at all the intermediate layers, not just the final softmax layer. We wanted to understand how important it was to train a very deep model. So we took all the layers of an ImageNet model, and we trained different types of classifiers on top, SVMs and a softmax classifier. So the SVM, starting from layer 1, was already giving us about 25% accuracy. By layer 5, that's the last convolution layer, it was beating state-of-the-art by about 10%. And Caltech 101 is another variant of the same type of data, slightly easier task. And then just to confirm, we trained softmax classifiers, and you can see that because they're very similar models, they're both linear classifiers, they get the same type of results. And this is essentially very close to the results you saw in the other graph. So yeah, in summary, I showed a way to understand what these powerful models are doing and how to use them to better understand how to improve the performance of the models. So thank you, and yeah, Clarifai is always hiring. Thanks. Yep.
So you mentioned that kind of bounding boxes and things like that aren't complete by this, but it seems like you could use it as sort of a seed to grow that bounding box based on other things if you're getting it right.
Yeah, exactly. That's what that saliency paper actually tried to do, was not only get a blurry notion of saliency, but they tried to use segmentation algorithms afterwards to use the saliency as a seed to those algorithms and then really trace out the objects, and it worked pretty well.
And secondly, one of the challenges is that you sort of have a limited amount of labels and a limited amount of data to train with. Do you agree with that? It seems helpful to be able to go out to some of these sites that have already either classified data or to use the existing models to classify and then retrain based on larger sets of data. I was curious about that.
Yeah, it's definitely possible. I mean, the problem with so the question was, there's a lot of labeled data out there. Can we utilize it, and can we utilize a trained model to help clean it up? And I think the answer is yes. And it's varying depending on what source it's coming from. Different sources like social media are very noisy, but there's so much more content there that the noise kind of washes out if you train a big enough model and for long enough. But there's also much cleaner sources, and then there's always manual labeling, which you can do to get perfect sources.
So it looks like there's some power in the features that are at some of the lower levels, showing SVMs, using those to get better accuracy. Do you have some of those in your final model and put those into the fully connected layers? Or is there a way of
So the question was, the lower layers show a decent amount of performance in classification, and he was asking if we use that in higher layers or near the classification, the final outputs of the classifier. We haven't tried that yet. We are working on a bunch of different architectures, but that's not one of them. I think there's a lot more information in the higher layers just because they've extracted it out so many more times, that feeding in very low-level information might hurt the classification, but different types of information might help a lot. Yep.
Also about that, the slide with the support vector between different layers. So at layer 5, you have 86%, and then at layer 7, it drops it. Is that just an artifact where you sort of hit convergence and that's just a little bit of noise in there, or is there actually a number of layers that is optimal and then you go above that, you start losing accuracy?
That's a good question. So he was pointing out that layer 5 with SVM was performing better than layer 7. So layer 5 is the last convolution layer, and layer 6 was a fully connected layer, taking all the information from that last convolution layer and producing a 1 by k output. And then layer 7 was, again, fully connected. So it could be that collapsing lost a bit of information, but it's also a lot different when you look at softmax. It didn't perform, right? It performed in the way you'd expect, where the 5th layer is performing worse. And also in the harder data set, the ordering was kind of consistent. So it could be an anomaly of that SVM just getting a good initialization. I don't know.
Could it just be that SVMs are better at classifying information than the network you're using for the classification at the top?
It could be, but it's not really consistent with theory or kind of the rest of the results, because they're both doing linear classifications essentially. There's some tricks with SVMs to make them nonlinear, but you can use different nonlinearities in your neural nets as well. So in essence, they're really doing the same thing.
Just curious to know what kind of hardware platform you're using for training as well as classification.
So we do everything on GPUs, kind of the top-end GPUs you can buy. And it's crucial. It gives literally a 30 times speed up over CPUs.
And is training time a bottleneck for you? And is that something you face with the difficulty scaling up your models and data sets?
So the question was, is training time becoming a bottleneck? I mean, as we always get more and more data, and it's literally orders of magnitude more data that we're collecting, it is becoming a bottleneck. But there's a lot of research going on about parallelizing these networks. And it's kind of at this point, it's a well-known problem of how to do that. It's not perfectly linear by any means, but it can definitely speed up the training significantly. So that's in the roadmap, at least. Yep.
And what interface are you using to interact with the GPUs, like CUDA or ML? What is it? OpenML?
So we're doing all the programming on the GPUs with CUDA, but we have implemented a bunch of different ways for different hardware. But CUDA is the main one we train on. So we wrote everything in-house. Yeah.
C?
C and Python. Yeah. Yep.
How well is your more thematic class? So could it find like the gloomy pictures and train it on gloomy versus absence of gloomy?
Yeah, so the question was about less concrete classes like gloomy. So it can recognize a variety of different categories. We see blur come out, we see abandoned come out, very subtle things that happen in images. Even fun or togetherness, which you see when people are close together holding hands or kissing, that is recognized. Yep.
You have different layers of detail in box sizes, convolution, right? Are those swept or are those discrete of each other on a rigid frame? Like when you pick a size, is it sweeping through the whole entire thing, pixel by pixel, or is it like a rigid grid?
So the question was how the convolutions are applied over the image and other layers. So it depends on the layer, but it comes down to two parameters. One is the size of the filter, and one is the stride between where you apply the filter. So in lower layers, we do strides of 2 because there's so much spatial content that we can't compute it at every location. It's too expensive. So we do stride 2. So it takes literally the top corner pixel and then skips one and then applies the whole template at the next.
So there is overlap between them?
Yeah, because the filters are like 7 by 7, but the stride is 2. So there's 5 overlap in every case. Yeah. Yep.
I know you're also working on video. Could you just say a little bit about how you work with the temporal information? So how you can is it sort of a silo for each frame that is somehow then fused together, or do you have some other way to communicate with the temporal information?
Unfortunately, that's confidential. Yep.
Have you done any with 3D images or by?
Not yet, but we've been talking to a lot of people in the medical space about 3D images and scans. It's very interesting, and it could really help out in that area. Yep.
Do you believe beyond just speeding up the training process, increasing the stride has advantages, or basically you want to go as low as you can?
Yeah, I think you really want to go as low as you can because you lose a lot of information by skipping. And you can see that in some of the results from this year's competition. They did even lower strides in the first couple layers, and it improved quite a bit. There's a bunch of new ideas introduced, but I think that was a really important one. Yep.
Have you found that there's a balance to strike between the amount of unsupervised training you do at the lower layers before you start doing the back propagation, and does visualization help with that?
So as regarding unsupervised learning in the first few layers, so we actually don't do any unsupervised learning in this. It's all just taking random filters in all the layers and training with the output categories.
So how do you get these new categories, like abandoned? Are you adding those in? Or?
Yeah, so that's in our vocabulary. All these descriptive words like abandoned are already baked into the vocabulary.